Welcome back. We are looking at interpolation of functions given by Lagrange polynomials. And in our last lecture, we studied the error form, and we now begin with seeing how this error form can be used to write down information about some given function. So let me share my slides. All right, so I hope you see these slides. This is our lecture number 12. We are finishing third week of this course. Let's recall what the error form is. Suppose we have a function which is n plus 1 times differentiable on some closed interval AB. Then whenever you choose these n plus 1 distinct nodes, so these are the distinct points, these are elements of the interval AB, x0, x1, x2 up to xn, and you have a polynomial p interpolating your given function at these points, then the error term is given by this particular formula. And I told you in our last lecture itself that this formula is very much similar to the Taylor polynomials error term, where you will have all the x0, x1, x2, xn to be the same points, and so you will have x minus x0 power n plus 1. That's what you are going to have. So this formula is very similar, and so if you remember the Taylor formula error term, then this will be easier to remember from that. And this xi x depends on x. In Taylor's error term, we had that this xi x was between the point x you are looking at for computing the error and the point x0. Whereas here we can only say that it is somewhere between the interval spanned by x0, x1, xn and x. It's just in that interval. So you will say that it's there in the interval AB. But it depends on your point x. This is what we have. So let's see, in our last lecture, we saw that we could compute this error term. The maximum error term could be computed. And here now what we are going to do is that we want to prepare a table. We want to prepare data for a function. And we are allowed to have the error within some prescribed bounds. And we will use that to see what the nodes have to be. So we are now going to work backwards. Once we know we are given a function f and we know what our error should be, that will tell us how many nodes we have to take and how the polynomials need to be taken. So that's the example, and really it's a question, which is that we want to prepare a table for the values of the exponential function on the interval 0 to 1. Suppose our nodes have a uniform behavior. They are the 0th node is 0, then the first node is h, then the second node is 2h, 3h, blah, 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 and you will have ih and dot, dot, dot. How many nodes are to be taken? That will depend on the value h, and that's the value we want to compute towards the end. But we also put one more condition, which is that between each successive nodes, each successive pair of nodes, xi and xi plus 1, we are interpolating our given function by a linear polynomial so that our computations are easier. Okay, so we will interpolate our function by a linear polynomial. Okay, so there will be these many linear polynomials from x0 to h. You will have a line which will join those 2 points. Then h to 2h, you will have another line, then another line. So you have a piecewise linear polynomial interpolation for your function, exponential function. And the question is, what step size h has to be chosen so that this interpolation is within the error 10 power minus 4 for all x. So what we will have to do is that we will have to compute those nodal values. We will have to compute the linear polynomial, joining them. And then whenever you want to compute the exponential function value at any point, you simply compute it for that particular linear polynomial. And we will have ensured that h is such that this error cannot go beyond 10 power minus 4. This is what we have to do. So what is the step value h that will ensure this? This is something that we want to do. So start with an x. Suppose you have started with an x, and then this x has to be between two successive nodes, so xj and xj plus 1. Okay. And let P be the linear polynomial which interpolates your function on these two, between these two nodes. So on the interval xj, xj plus 1. Xj, xj plus 1, we have this linear polynomial interpolating our given function. Then there is this error form. Because you are looking at the linear polynomial, the error form will involve second derivative at the point xi, which is dependent on x. Okay, so the error form, the mod of fx minus px is less than or equal to mod of, actually this mod of fx minus px is equal to this, so I should have said equal to f2, the second derivative at xi, upon 2 x minus xj, x minus xj plus 1. This is the value we get. But this is further equal to, we will put the modulus for the second derivative of the function at xi and the polynomial part that you have. The modulus for the second derivative part can be easily computed. Its second derivative, you are looking at the function f of x equal to e power x. So that's going to be e power xi. Okay. And therefore the maximum of the second derivative on xi is going to be less than or equal to the maximum taken over the whole interval. Okay, so that's going to be less than or equal to maximum of the exponential function taken over the whole interval, which is just e. So that part is computed now, that is e by 2. And you have to compute the maximum of the second part, which looks like the polynomial x minus a into x minus b. That's how this polynomial looks like. And on that interval AB, we want to compute the maximum of its modulus value, the maximum absolute value. So this is what we want to now find. Remember, there is an e by 2 outside, and we will have to multiply by this maximum value of x minus jh, x minus j plus 1 h. In fact, there will be an h which would have come if you had just computed this maximum of the second derivative at xi, but that would be an exponential form, and so instead of putting an h there also, we have just taken the maximum of the whole exponential function at 0, 1, and then our h will come from the polynomial, where it would be easier to do the further computations. Okay, so our polynomial is gx, which is x minus jh, x minus j plus 1 h, and we want to compute the maximum value of its modulus. So you want to compute the maximum and the minimum value of the polynomial. I told you that it looks like x minus a into x minus b. So this polynomial has the property that on a and on b, the values are 0. And between a and b, suppose you take an x between a and b, then x is bigger than a because you have gone beyond a. So x minus a will be a positive quantity, but x is still less than b. So x minus b is negative, and therefore the value between a and b will always be negative. This polynomial x minus a, x minus b, these are some of the most easiest examples to plot, because they will have the value 0 on a, 0 on b. Between a and b, it will have a uniform, nice symmetric behavior, but below the x-axis, and before a, both the x minus a, x minus b are negative, so their product is positive, and after b also x minus a, x minus b are positive, so the product is positive. So it looks like a parabola which will pass through the point a comma 0 and b comma 0. Okay, and therefore the minimum value needs to be computed, which will be the maximum value for the modulus of gx. So the derivative computation gives you this. I told you that it's a symmetric graph, therefore the minimum value is going to be achieved exactly at the midpoint, which will be a plus b by 2, which in this case is jh plus h by 2. And then the value at that point can be computed once again easily, which is minus of h squared by 4. Okay, so I have this polynomial gx, which is x minus jh into x minus j plus 1h. That's the polynomial, and its maximum modulus, the maximum absolute value, is to be computed on the interval jh, j plus 1h, and we see that its minimum value, because there is only one critical point, minus of h square by 4 is the minimum value, and the function has 0 on the endpoints. So if you were to take the maximum value of the modulus, it will be h squared by 4. Okay, and so what we get is that the error now fx minus px is less than or equal to, remember that e by 2 we have from the previous slide, into the maximum value of the modulus of gx, which is h square by 4, and so we have e h square by 8 at the end. And we want this maximum value of the error to be less than or equal to 10 power minus 4. So e h square by 8 has to be less equal 10 power minus 4. You multiply by 8 on both sides, divide by e on both sides. That gives you h square to be less than or equal to some quantity. Take the square root and it gives you that h has to be less than or equal to 0.0171. Now this h has to be something which is 1 upon an integer. So we take h to be 1 upon 59 and that will work. So you will have to compute exponential values for the 60 rational numbers: 0, 1 by 59, 2 by 59, 3 by 59, dot, 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 59 by 59, which is 1. And then there is a, you will join these points on the, in the plane by straight lines. And then any point, for any point between 0 and 1, you simply compute the value of this piecewise linear interpolation. That will be your e power x up to, which will be correct up to first few decimal points. You know, it is less than or equal to 10 power minus 4. So that gives you that the value is going to be correct up to first nice number of decimals. This is how we use our error form to compute the value of a given function by choosing a suitable size of the steps. That's the step size, which is h. Now, there is a practical difficulty with Lagrange polynomials, and let me outline it for you. So observe, first of all, we did not really compute the linear interpolating polynomial in the previous example, but we have made explicit use of the information about the function f. So knowing that the function was our exponential function is very important for us, because only after that we can compute the error form. It depends on some certain derivative of the function on some point in between your x, x0, x1, x2 up to xn. So you have to know about the function, you have to know about its derivatives and so on to be able to compute the error form. Typically, what would happen is that you would be given only some data without any information about the function. Our original example, if you remember, was about census of our nation, and that we don't know what function it follows. We just have a data of tables corresponding to the population for given period of years. For the 1951, 1961, blah, 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 we have only the population. And we don't know what function it satisfies. So it will be similar to the data we have here. And suppose from this data, we want to compute or estimate the value at 1.5 by various interpolating polynomials. This is what we want to do. Then how do we go about doing it? So first of all, we see that there were, the nodes were 1, 1.3, 1.6, 1.9 and 2.2. So they were changing, the step size here is 0.3. Okay. And we find that 1.5 is lying between these two nodes, 1.3 and 1.6. These are the two successive nodes which contain our point 1.5. So if I were to take a linear polynomial which is interpolating this given data and I want to compute its value on 1.5, then it is sensible to take the linear polynomial for the nodes 1.3 and 1.6 because 1.5 is between them. So we take this linear polynomial P1, which interpolates our function on the interval 1.3 to 1.6, and the value at 1.5 of this polynomial, which I leave for you to check, is 0.510298. That's the value. Okay. Now we go to quadratic polynomials. So we will need 3 nodes. Ideally, these three nodes should be such that they contain 1.5. So there are two possibilities. You can look at 1, 1.3, 1.6, and you may also look at 1.3, 1.6, 1.9. These are the intervals which contain our point 1.5. So we have these two quadratic polynomials which interpolate our data on the two intervals 1 to 1.6 and 1.3 to 1.9. And their values are changing a bit, right? We have 0.5124715 and 0.5112857. This is what is happening for P2. If you were looking at 3-degree polynomials, then we need 4 data points, 4 nodes. And once again, there are possibilities, 2 of them, which is 1, 1.3, 1.6, 1.9, and 1.3, 1.6, 1.9, 2.2. So there are 2 cubic polynomials, once again, P3 and Q3, interpolating our function or let's say our data on these two intervals, and their values are given below. So we see that P3 and Q3, the values are quite close to each other. If you see starting from Q2 to P3, Q3, the values are remaining the same for first 3 digits, 0.511. But for P3, it is 0.5118. So it's even these two are the same even for the first 4 digits after the decimal points. So for 4 significant digits, you have the same value. Let's go one step ahead and compute the quartic polynomial on the whole data, that is P4, and it gives you again something very similar, 0.511820. So starting from P1 and going to P2, Q2, we saw that there was a sizable change. From P2, Q2 to P3, Q3, again there is a sizable change. But P3, Q3 to P4, the change is not much. Meaning, you had 5118127 and 5118302, and P4 again remains 5118200, which is roughly the average of these two. So we can say that these last 3 entries are somewhat reasonable estimates. They are the reasonable approximations to f of 1.5, and among them we can take the last one, because it is first of all also the average of the other two correct values, and also because it uses the whole data. So once it uses the whole data, it gives you a better approximation for the function value at 1.5. But to find this, we had to go all the way up to P4, right? And one practical difficulty with this, so we have been giving the slide titles practical difficulty, but this is the first time we are explicitly pointing it out, that the computation of the smaller degree polynomials did not seem to help the computation of the higher degree polynomials. When we ultimately wanted to do P4 computation, we had to start from scratch. We had to compute the Lagrange polynomials, and then we could go and compute the polynomial P4. That is what we had to do. So the computation of the smaller degree polynomials did not seem to help. And we would like to find a method which helps in computing the Lagrange polynomials or even the interpolating polynomials in a cumulative way. Is there a way that the smaller degree polynomials will help you compute the larger degree polynomials, the higher degree polynomials? So let's start again with some examples. We want to do the cumulative calculation of interpolating polynomials. Suppose we have a data given on these distinct nodes, x0, x1 up to xn. And for the node x0 and the node x1, we have constant polynomials. These are the degree 0 polynomials, which are p0, which is f of x0, and q0, which is f of x1. So p0 is the degree 0 polynomial which interpolates our function on the singleton x0, and q0 is the degree 0 polynomial, constant polynomial, which interpolates our function on the singleton x1. And how do you get the linear polynomial which interpolates the function on x0 and x1? The formula which you know quite well by now. Here we have the Lagrange polynomial, which has value 0 on x1 and 1 on x0. And to that polynomial, we multiply by the function value at x0. And similarly, here we have the Lagrange polynomial, which has the value 0 on x0, 1 on x1, and we multiply by the function value at x1. We will notice that the denominators have the same value, except that there is a sign change. So if we just put the denominator here same, and observe that f of x0 is nothing but our polynomial p0 at x, and f of x1 is just q0 of x. Then we get x minus x0 p0 x minus x, x minus x1 p0 x minus x minus x0 q0 x, whole thing divided by x0 minus x1. So we got the interpolating polynomial p1 from the interpolating polynomials for x0 and x1 and the information about x0 and x1. That's the only thing we had to use. We did not use anything else. Can we generalize this to a formula? So this initial calculation might be difficult to generalize. Let's do one more case. We will do the quadratic case. So what that means is that we will start with linear polynomials interpolating x0, x1, x1, x2, and we will try to see whether we can write down the quadratic polynomials on these three, x0, x1, x2. So for nodes x0 and x1, our linear polynomial is this, right? It's the Lagrange polynomial for x0, x1 into f of x0, Lagrange polynomial for x0, x1, but the value is 1 now at x1 into f of x1. The same for x1 and x2 is this. So we call them p1x and q1x. These are two linear polynomials. And the quadratic polynomial for x0, x1 and x2 is this polynomial, right? Here we have f of x0 into the Lagrange polynomial, which has value 1 on x0 and 0 on x1 and x2. They multiplied the coefficient of f of x1 is the Lagrange polynomial, which has value 1 on x1, but it's 0 on x0 and x2. And finally, the coefficient of fx2 is the Lagrange polynomial whose value on x2 is 1, but it vanishes on x0 and x1. So this is our formula for P2, and let's rewrite this P2 in a slightly better way. So we note that P2 is given in this way. Okay, I have just copied it from the previous slide, but I am going to write it in a slightly different way. I have made some changes, and let's just verify that these two expressions are still the same. Let's compute the coefficient of f of x0. Here it is x minus x1, x minus x2. In the numerator, we indeed have x minus x2, x minus x1. The denominator for f of x0 is x0 minus x1, x0 minus x2, which is really the thing here, x0 minus x2, x0 minus x1. Okay, so f of x0 component is correct. Similarly, fx2 component can be checked. You have x minus x0, x minus x1. Here outside you have x minus x0. There is a negative sign. Okay, we will think about that. The numerator at least is x minus x0 and x minus x1. Numerator seems to be correct. The denominator is x2 minus x0 and x2 minus x1. x2 minus x1 has come all right, but x2 minus x0 has become x0 minus x2, and indeed with the negative sign that would have been taken care of. So f of x0 component is correct, f of x2 component is correct. Now f of x1 has come twice. That needs to be seen carefully. The numerator is simpler because it is x minus x0, x minus x2, which has come in both of these parts wherever we have fx1, x minus x0, x minus x2. Without any change in the order, it has come. So the minus sign has still to be taken into consideration. Let's look at the denominator. The denominator here is x1 minus x0, x1 minus x2. x1 minus x0 has come with x0 minus x2. So there is, instead of x1 minus x2, we have got an x1 x0 minus x2. But the x0 minus x2 is coming for both the instances of f of x1. So this numerator of f of x1 into the numerator of the f of x1 component into f of x1, that is all right. For the remaining part, 1 upon x0 minus x2 is again constant. So we put that also outside. And now what we are left with is 1 upon x1 minus x0 minus 1 upon x1 minus x2. Okay, so 1 upon x1 minus x0 minus 1 upon x1 minus x2. When you compute this final value, the denominator is the denominator that you were looking for, x1 minus x0 and x1 minus x2. Okay, so we have to now find the correct numerator for that subtraction, for the difference. That would be x1 minus x2 minus x1 plus x0, because the x1 minus x0 now it will come with the negative sign. So it is x1 minus x2 minus x1 plus x0, and that gives you x0 minus x2, which is really the x0 minus x2 in the denominator. So if you write it down and see that these two expressions of p2x are correct, but the thing we have here in the first square bracket, this is the linear polynomial interpolating the function at x0 and x1. And the thing in the second square bracket is the linear polynomial interpolating your function and at x1 and x2. So we again have a similar formula. X minus x2 into p1x minus x minus x0 q1x, and the denominator is same, x0 minus x2. Okay, so let's summarize. What we had was p0 and q0 interpolated our function on x0 and x1 respectively, and then p1, which was interpolating our function on the union of these two singletons, is given by that formula. P1 interpolated the function on x0 and x1, q1 interpolated it on x1 and x2, then P2 interpolating on the whole x0, x1, x2 is given by a similar formula. So for P1 to P2, we had replaced x1 by x2. x1 is replaced by x2. That seems to be the only change. And let me end this lecture with a question for you, that we are now going to the higher case. We have P2, which interpolates our function on the triple x0, x1, x2, and we have Q2, which interpolates it on x1, x2, and x3. And then there is a P3, which interpolates it on the union x0, x1, x2, x3. Do you get P3x equal to x minus x3 P2x minus x minus x0 Q2x upon x0 minus x3? So in our next lecture, which will be released in 2 or 3 days, I will give the answer, and I will also tell you about the general form of this formula. But this simple problem is a delightful thing to solve, and I really urge you to think about it and let me know your answers on the Google Classrooms. So thank you, and we stop at this point.